Okay, we're going to start with section 9.3 today. We'll address the last part of section 9.2 when I get back, okay? All right, so today we're going to go over how we state and check the random 10% normal large sampling conditions for performing a SIG test about a population mean. The conditions are going to be a carryover from section 8.3 and chapter 7 as well. All right, and then we'll get into the beginning stages of the SIG test for a population mean. All right, so I'd like you to pause the video right now and read page 574 and all the way through 575, and then we'll come back together for this example. Go ahead. Okay, the part that really probably is worthy of a little more follow-up is the normal large sample. Remember, there's three things going on here. If the population has a normal distribution, then so will the sampling distribution. Okay, so we can move forward. If that's not the case, if it's not stated, we know the sampling distribution will be approximately normal if the sample size is at least 30. Okay, but if that doesn't happen and we have smaller samples under 30, we can still move forward as long as the sample data doesn't show strong skewness or outliers. Okay, so that's what's happening in this example. They sampled 15 batteries. That's not high enough. They didn't say the population was normal to begin with, so we need to look at the sample data. Okay, now they gave us more than what we need. This is usually my recommendation, just use the box plot. All right, now although it does look like it's a little skewed right, but not strong enough to throw out, no outliers. So as they're stating here, this is an important statement, we should be safe performing a t-test about the population mean. Okay, so we can use T calculations is another way to phrase that. All right, so in short, remember with means are more volatile than proportions. We had that tomato example back in the beginning of 8.3. I'm not going to flip back and show it to you, but remember, we had a problem. Our capture rate wasn't matching up with what it should be with means. So the solution to that was to use a new distribution, which had bigger critical values, all right, when compared to the Z critical values. That's all. That's really all you got to know, and then we got to know how to use it, okay? So here's how we're going to get our test statistic for these means. This is in your notes too on the first page right here. Your test statistic will be the sample mean minus the parameter. That'll be the null hypothesis mean, okay, and then over the standard error. Okay, and we don't have the population standard deviation, so we're going to have to use this. All right, we're using a t distribution with n-1 degrees of freedom. Okay, so let's take a look at example 15 in your notes, which is also on page 577, and I'll show you how we figure this out. All right, so go ahead and read this setting, and I'll show you what's going on. Pause and do that. Okay, so just like in section 9.2, we get a sample. It's not 30, but is it statistically significant or not? So we're going to do the math. We're going to find the probability of getting a sample of 33.9 hours and then use that probability to make a decision of whether or not we reject H of O. Okay? All right, so here we go. Sample mean minus 30 divided by the standard error, we get 1.54. Okay, so that's the T critical value, 1.54. So we want to find the likelihood. We need to find the shaded area, right? That's what the p-value is. What's the likelihood of getting a test statistic of 1.54 or higher? It's standardized, right? This also means 33.9 hours or higher. Okay, so there's two ways we can do this. We can use the table B. If you don't have this in front of you, I'd pause the video and grab your yellow packet so you can follow along and track this, okay? Okay, so remember how the table B is a little different than table A. Table A, the normal distribution, the areas are here, and the Z critical values are on the outer edge. T distribution is a little different. The critical values are in the middle of the table, and the tail probability is actually located up top. We haven't used these before. We just kind of paid attention to the confidence levels down here. All right, but that kind of makes sense, right? Confidence levels of 95% means there's 0.025 on each side of the tails, and look what it says for tail probability up here. Okay. All right, so let me show you how we're going to read this. The degrees of freedom for this problem is 15 minus 1, so 14. Okay, so we need to look to the 14th row to find our t critical value. Okay, but how do I do that? All right, so 1.54, I'm just trying to remember these values. Degrees of freedom 14. 1.54 is between these two critical values. So here's the assumption we can make, that if it's between these two, that the tail probability must be between 0.05 and 0.10. Okay, so that's how we read that. Find where your critical values, if it's our critical value is right on 1.35, we can say, all right, the probability is 0.10. But it's between this range, so we're just going to use that as our range of probability. Okay, so that's kind of the conclusion. We know that the p-value is between 0.05 and 0.10, or maybe you want to make an inequality for that. Something like this would work too. Okay, all right, and that's usually enough to make a decision on the SIG test, right? So if it's between 5 and 10%, maybe 7 or 8%, then we can make a decision on a SIG level of 0.05. All right, but if we want to pinpoint this, we can also use TCDF, just the same as we would normal CDF. Okay, pause it if you want to write that down. I'm going to grab my calculator and demonstrate this. Distribution, right underneath the normal CDF, a few rows down, we got the TCDF. I think I already have it punched in here. Yep, so 1.54 is my lower bound, right? Or left bound's another way to think of that. And then just choose a high critical value way out here. I went a little extreme. 1,000 is plenty. Even 10 would be plenty. And then report your degrees of freedom. Okay? It's going to paste it in the screen, and it gives me the p-value. About 7.3% chance, right? Which makes sense with what we were assuming. All right. So there we go. That's how we find the p-value for these t-distributions. Table or technology, your call. It doesn't really matter. Okay, let's go ahead and go on to the next page. I want you to read the example on page 578. They go to a two-sided test now. The one we just talked about, the battery life was one-sided. So I want you to read that. I'll talk about a couple things there. We'll also take a look at the technology steps and then wrap up today's lesson with the check your understanding. Okay? Pause and do that. Okay, let me try to unwrap this a little bit for you. Even when we are creating confidence intervals with this t-distribution, if we're caught in between numbers, we always went up higher to make the critical value higher. Because if we take a little glance at this and you look up, the critical values get larger, right? As we go up. So we needed a larger critical value to make sure our capture rate was good. We don't want to go down and then make our confidence interval smaller and then our capture rate's not living up to advertised. So you kind of do the same thing. So we're kind of already used to going up, all right? And that's what they're saying, we still go up, all right? So when we have degrees of freedom 36, instead of going down to 40, we go up on the chart to 30, okay? All right, so then we do the same thing. Here's a nice little snippet of it, so I don't have to put that yellow sheet underneath here again. So we're looking for 3.17. It falls between here. So if we look up to the p-values, it's between 0.001 and 0.0025. Okay, but if it's two-sided, remember, this doesn't give you negative critical values, only positive, but it's okay. It's symmetric. So we just get that value for positive 3.17, and then we assume it's the same on the other side of the tail, and we just double that. So that's what happened here. They took the 0.001 and 0.0025, that range, double your lower bound, and then double your upper bound of that probability. So basically, we expect this to be between 0.002 and 0.005. Okay? But they're also telling you, okay, well, the best advice is just to use technology for these complicated issues. Absolutely. Just use TCDF. Okay, so if we do TCDF, well, they have it right here. Punch that in, 1.54. Actually, that's not the same example, is it? So let me do this real quick. Again, it's going to be I'll just type over this. Degrees of freedom. We can actually punch in the exact amount now. You don't need to decide go up or down. You can just use 36. So 36, and then my test statistic was 3.17. And we get this small value. This is just one tail, so I would double it. And there we go, 0.003. Does that match what we had written down? Yep, that's between 0.002 and 0.005. Okay? Okay, so to wrap this up, I want you to try this check your understanding. Okay, I'll give you some feedback as well as soon as you're done, but this is going to take a good 5 minutes. So pause and take yourself through that right now. Maybe even work with somebody nearby if you want to on that. This flow looks familiar, right? Or it looks familiar. You know, the state plan do conclude is what they're pretty much walking you through. Okay, so pause if I'm going too fast, but I'm going to go fast because I know you can pause. They didn't say which sig level to use, so let's use 0.05, okay? Notice this is a two-sided test, so we're going to be interested in finding the area to the left of -2, critical value, and +2. The table only gives me this, so we'll double it. So degrees of freedom is 35 if you're using your calculator, but if you're using your table, you're going to use 30. It's up to you. If you use the table, they'll write that down. Okay? So we could report it this way. Oh, I'm sorry. Then we got to double it. Two-sided test. It's between 0.05 and 0.10 after we double it. All right, and then here's the technology. Get this value, then times 2, it's 0.0534. Okay, and then they said the conclusion. So I tried squeezing it in here, but it's greater than 0.05, so we fail to reject H of O. There is not convincing evidence that the true mean amount of active ingredients contained in these tablets differs from 320. Okay, that's it for today.